Good evening, folks. For those of you who don't know me, my name's Chris Wenzel. I'm the current LIAPG president, and welcome to our August webinar. We've been doing these monthly throughout the year and hope to continue to do so through December. Before we get to our main event, a few announcements here and get our slides going. Of course, we always have to thank our corporate sponsors for 2021. We have two levels, Diamond and Topaz, and our sponsors are Cascade Environmental and Drilling, PW Grosser, Alpha Analytical, EnviroTrack, ERM, Island Pump and Tank, Regenesis, VHB, and York Analytical. And as always, we thank our sponsors for all that you do for us. You certainly help us keep the LIAPG going, our website, our insurance, and things like that that factor into a budget that you need to have for an organization to keep going. So just some announcements, upcoming events. As I mentioned, we've been doing these Zoom meetings monthly until we can get back together face to face and folks are comfortable with that. We have one more scheduled for Q3 of 2021. That's on September 23rd. Dennis Askins, who's with the New York City Department of Design and Construction, he's spoken at our events before. He's going to do a presentation on the role of geologists in New York City. And I certainly encourage you to attend if you can. Dennis is a wealth of knowledge when it comes to New York City and information that is hard to come by, and he is always looking to help folks. So it should be a good presentation. We're looking for more speakers for the remainder of the year. We have slots open for October, November, and December. And my appeal is that anybody who has anything interesting, and if you've participated in these before, it's casual, but we'd love to have folks come out. Content is very flexible. We like to have variety. That's what keeps it interesting. So please, if you do have something, reach out to us. You can email us. You go to our website, you can email us, you can call me. Lots of ways to get a hold of us. As far as field trips, at the present time, we were originally contemplating putting together a fall field trip or two, and there hasn't been a significant amount of interest in it in light of a little bit of a spike in COVID. And so right now they're on hold. If the general group is really interested in doing something, reach out to us. And if there's a strong interest, we could put something together. It probably would be an outdoor event, if anything. And then lastly on this slide, the LIAPG board, we're an open organization. We meet online right now, but typically we meet on the first Monday of every month. In September, it'll be on the 13th instead of the 6th. As a result of some vacations coming up. But if you're interested in seeing what goes on, getting involved, we can easily send you a Zoom invite and get you in there with us. So think about it. Oops, wrong way. We've shown this slide before, and it's really just an example to show you some of our other organizations in the region, and they all have activities and events that go on. It tends to be a little bit of our sister organizations take a break in the summer, but as you can see here, starting at the top, the New York State Council of Professional Geologists, they've been working on getting licensed by the New York State Education Department to offer continuing education credits courses for what will be requirements for any of you that have a New York State PG license. There is a event that they've been putting together, supposed to be September 22nd, and it was in, I think, White Plains last time at a place called the Coliseum. And there's not much on the website yet, but there is, if you go to the LinkedIn page, it is a fish cover band, and I believe Lithology Brewing is, sponsoring beer there. So stay tuned, look for that. As I said with the other organizations, Buffalo, Central New York, Hudson Mohawk, and the AIPG, they all have events. I checked their websites today. It all says, check back soon. Probably in September, they'll get back into the groove with it a bit. Tomorrow, there's an event online put on by Midwest Geosciences Group. Probably many of you are aware of them. They have a online webinar tomorrow, 4 p.m. Eastern, the geology of beer. I believe it's no, I'm sorry, it's 5 p.m. Eastern. And you can still sign up for it. And if you're really interested, you might have seen the notice that went out last night that at Lithology Brewing in Farmingdale, they're having a watch party if you want to go down there and check it out there. Just a few more. As I said, there's awful lot of content out there if you just seek it out, but besides what we do. SUNY Stony Brook has geology open nights. They also do astronomy and some other physics. Right now, they haven't put out their calendar for the fall, but check back there because they typically have 3 or 4 a semester. And some of the topics, if you look on the website that they've done, are really cool stuff. So take a look there. And I mentioned before, Pennsylvania Council of Professional Geologists, they have a lot going on year round. And you can see here, they've got some upcoming webinars, the 24th of August, one on water chemistry as it relates to the Marcellus Shale. In September, there's one about karst site characterization, focusing on use of geophysics and geotech projects. There's one on the 23rd on urban and semi-urban watershed characterization. And then they've got one listed up there, which is an all-day event, 29th of March, 2022. It's the hydrostructural geology, and it's an in-person event in Eastern Pennsylvania. I forgot the name of the town, but you can go to their website and look at it. And if you're interested, sign up. It might be a good course for folks who want to learn more about hydrogeology and structural geology. That might be cool. Lastly, as you know, at this point, there's no grandfathering into a professional geologist license, and you need to pass the both parts of the ASBOG exams. And here is listed is the next exam is in March. There's one in October, but the application deadline's since passed. So you would have to sign up for the March event, and that is November 15th. And then there's another one, it's given twice a year in October. Deadline for signing up there is June 2022. You can go to their website and check it out. And now, probably tired of hearing me, so we're on to the main event. Eliot Cooper from Cascade Environmental is going to make a presentation on injection chemistry products that are available to treat DNAPL source areas. So with that, I'm going to stop sharing and let Eliot pick up where I left off. Thank you, Eliot, and welcome.
Yeah, thank you. Let me share my screen.
Yeah.
Right there. You see my screen now, or?
Not yet.
Let's see.
What are we doing wrong here?
I think I just need to share it. Listen.
Yeah.
There I go. Let's see.
You're definitely listed as a co-host, so you're good there.
You see that one?
Yes, it's coming up.
How about that?
Yep.
Cool. Well, thanks for the opportunity to speak tonight. I'm actually coming to you live from Del Rio, Texas. And if you haven't been there, you're lucky. So, but it's an Air Force base, and they've got some contamination that needs to be cleaned up. So today I'm really going to focus on chlorinated solvents, and particularly DNAPL, and some technology that we have that can be applied to DNAPL sites. And so wanted to introduce that to you. That's a picture of me, but I'm also on the screen there. So skip that. The agenda is going to be talk about the evolution and science behind ZVI, zero valent iron, and emulsified zero valent iron. And on the right, there's how the product comes. It comes in 250-gallon totes. It's 10% zero valent iron, and the remainder emulsified vegetable oil. And it's kind of a viscous chocolate pudding material, as you can see in the beaker there. I'm going to talk about whether or not you have a DNAPL issue. And then finally, how do you inject this material in the ground? Some case studies about it, and then why we're seeing the adoption of EZVI starting to increase again. And since this product was launched about 20 years ago, and so you may be familiar with it, and you may not. So, but we're starting to see more interest in this product. So one thing about DNAPL that's interesting is it's a big problem. And if we look at the most recent report about sites not achieving closure with chlorinated solvents, we can see here it's a very large market. There's still over 126,000 sites that have contamination in the ground. It's estimated that to actually clean all these up would be billions of dollars. And you can see they range, you know, from public and private sectors. So, so it's a big market, and that's why, you know, we all should be interested in this challenge of cleaning these up. The chemistry is pretty well understood. It's been around for a long time. There's actually two pathways for ZVI. There's a beta elimination pathway, which takes your chlorinated solvent like TCE and reduces it to chloracetylene, to acetylene, and then to ethene. And generally, that's the major pathway that's occurring, but there is still some hydrogen generated in the process. And so you can get a much smaller pathway that's going to go through the standard anaerobic dechlorination pathway, which would be to cis DCE, vinyl chloride, and ethene. So something to consider when you're applying the technology, that there is a potential for forming some daughter products, and you just need to design around that. The basic chemistry is the same regardless of the particle size, whether or not it's a grindable material, whether it's microscale, which generally we look at 100 microns or less, to colloidal scale, which generally is the 5 microns or less, to nanoscale, which is, you know, below a micron in size. So what's happened over the years, and NASA was the first one who really jumped on this, because they discharged a lot of TCE in the ground at the Space Coast in Florida. And they did that because they had to flush out the rockets, the fuel, clean them out. So they had this big DNAPL problem, and they actually developed a technology called the emulsified zero valent iron to cost effectively treat that. And then, like any government agency, they eventually decided to license the technology to the commercial sector. And so, you know, ZVI by itself is very effective in treating contaminants in the dissolve phase, but they're really dependent on the dissolution and transport of the solvents. But they don't do anything to treat the actual product in the free phase or DNAPL phase. And so the DNAPL has to move it into the, through equilibrium into the water phase, and that's where it can be effectively treated. So if you have a site where you have a DNAPL and you just injected CVI or a chemical oxidant or a bioremediation compound, you're really only treating the dissolved phase. And that's why you can use the analogy, you're really chipping away at the iceberg. You're treating the dissolved phase and you're waiting for the DNAPL to move into the dissolved phase and treat it again. And so that's just takes a very long time frame. And so that's where the technology was developed to go after this source material. And you can see here a lot of the applications for ZVI was primarily in a permeable reactive barrier, and that was pretty much treating dissolved phase contaminants flowing through transmissive zones coming off of source areas. So the technology is really an emulsion droplet containing iron particles and water surrounded by an all liquid membrane. And there's a cartoon of that over to the right. So it's composed of the ZVI. In this case, it's a 5 micron size ZVI particle, a surfactant, a vegetable oil, and created as an emulsion. And originally the technology started out as a nanoscale iron. And the problem with the nanoscale iron was it was cost prohibitive, and it eventually slowed down the adoption of the technology. And so over the last 20 years, the technology folks involved with this technology started experimenting with larger particle size iron and found that it was just as effective and could be offered at a lower cost. So what happens is the DNAPL diffuses through the oil membrane, and then it's degraded in the presence of the zero valent iron in the interior aqueous phase. It, like I said, also contains a vegetable oil, in this case, soybean oil, and surfactants. So you also have a long-term anaerobic reaction going on with those electron donors. And then because you've got that anaerobic reaction, it's often recommended that when injecting EZVI into a DNAPL zone that you also bioaugment. So you would also inject some D. helicoides inoculum bacteria to make sure that the anaerobic pathway is not going to stall at DCE or vinyl chloride. And this just shows you kind of how the contact works with DNAPL. So we've got the DNAPL here dyed in red with a Sudan dye. And then we've added ZVI to it. And you can see that the ZVI and the NAPL are separate. But then when we add the EZVI, you can see that through the moving into the emulsion, it's totally miscible. So that's really, the high level view of why this is going to be effective at a chlorinated solvent DNAPL site. So advantages and limitations of this technology, and actually the product we have is called Source Kill that Cascade has. We provided through an exclusive license with a manufacturer called TEA out of Dustin, Florida, and they were one of the original licensees of the technology when NASA first came out with it. And we're heavily involved in the initial testing at the Cape and some of the DoD facilities back, about 15 years ago. So the advantage is you can treat DNAPL, so you can shorten the time to closure. You immediately get sequestration provided by the oil and degradation provided by the ZVI. So you do see quick results. You see a significant decrease in mass flux due to the VOC's partitioning into the oil. And then you also get long-term biodegradation provided by the oil. And like I said, bioaugmentation will enhance that. The limitations is this is a source technology, so it's not cost effective for for a plume or even a barrier, because you're not going to have DNAPL moving through your barrier just by the definition of DNAPL. And then you do have to have good characterization of your source area, because like anything, this is contact driven, and you've got to get this amendment in contact with the DNAPL. So you have to understand where that DNAPL is situated. So, just stepping back a little, do you have DNAPL? And I kind of, a similar question is, do you have matrix back diffusion issues? And, a lot of folks, don't think they do or hope they don't, but it's pretty prevalent. And we do a lot of high resolution projects, with this service Cascade offers. And based on years of doing these at chlorinated solvent sites across the country, we've actually developed some expert rules of where you might be moving into the high sorb mass. So a lot of mass sorbed to soil, which would, be indicative of you're going to have a matrix back diffusion design challenge, or to the DNAPL phase. And so based on the 4 detectors used in the MIHBT system, which is, as you know, a high resolution site characterization technology, we can get a good idea that you're getting into some hot stuff. And so we've got 4 detectors that we use. The XSD, which is a halogen specific detector. We've got a PID that'll measure double bonded compounds, which many of our chlorinated solvents are. The FID, which will measure combustible compounds. And when you get into high concentrations of chlorinated solvents, you will generate combustible products that the FID will pick up. Normally at low concentrations, it won't. And then we have the electron capture detector, which is really just specific to PCE and TCE, and it's very sensitive. So in most cases, we're going to see that ECD spike, and then we're going to start looking at the other detectors to get a better indication of how contaminated the site is. So, we measure these in microvolts, and if we start seeing detection limits in these ranges, in 500,000 microvolts to 1 million, to ECD, which is 10 to the 7th, we know we're getting into some hot stuff. So that's a great thing when you're looking at setting an expectation of what's going to take to clean up a site. It's important to really understand that. And of course, we do confirmation soil samples and groundwater samples to confirm and calibrate the MIP responses to actual field data. And then the other thing we look at, and this is not as big of an issue for the EZBI, because it is a product that we do have to fracture into the formation. But we do look at the electrical conductivity and the pressure from our hydraulic profiling tool. And if those start exceeding certain levels, we know that, we've got mass tied up into some finer grained material, which becomes an issue, if you don't want to fracture, or what kind of fracturing technology you're going to use. So these are kind of rules that we can use up front and really get a good idea of what you're dealing with in the source area, and also start to make some pretty good decisions about what kind of remedial approach you're going to undertake. So just to give you an example of how we did this, we had a project in California at the Alameda Navy base, and the client, in this case, it was Shaw, so it was done a few years back. I was looking at, was there a DNAPL source in this one site they've been working on for over 10 years. And so we went out there with a submarine. No, just kidding. We went out to this area, and we had a bunch of monitoring wells and we did some MIP out there. They had never identified DNAPL in the monitoring wells, but they knew they just weren't making a lot of progress. So they expected it or suspected it, and then wanted to see if we could confirm that with the MIP system at the time. And based on the investigation, we were able to pinpoint a potential DNAPL zone. And those squiggly lines are the detector responses, but I don't have the microvolts there, but they were above those expert rules that we had established. So we had a good idea that this is where we should sample and see whether or not we can confirm the presence of DNAPL. So as a result, we picked an area with the lighter red here as the potential DNAPL zone, but then we did our soil boring confirmations, and we eventually got down to that little area in the darker red as the source area for DNAPL. And like I said, the client here, after many years and a lot of wells, and we're never able to pinpoint the DNAPL source, but we're able to do this in about 5 days. And so the key here was we were able to do some soil sampling, and with a red dye, we're able to identify DNAPL in the soil. So at the end of the day, yeah, they had DNAPL, and we know where it is, and now they have a good shot at cleaning it up. Now, in this case, they did not use EZVI. In this case, they use a surfactant to pull the DNAPL out of the subsurface. So just a little bit, the reason we have to fracture this product in is because the diameter is greater than the pore space. And so we just can't inject it as a liquid. And like I said, it's a viscous material. So we do have to fracture this in and create pathways for it to move through the subsurface. So pretty similar to what we would do with a microscale ZVI if we were just injecting ZVI in like a PRB application. So the delivery, it's a little trickier than injecting liquids into the subsurface. If we're going into a high K zone, and we can figure all this stuff out with the MIHBP responses. So when we define an approach, we've got a good basis for it. So if we're going into high K zones, we have better distribution using a hydraulic fracturing approach. If we're going into a low K zone, we can use hydraulic or pneumatic fracturing, and I'll get into those in a little more detail. And if we're going into a heterogeneous area, that's typically what we're gonna see, typically having better success with a hydraulic fracturing approach. So here's an example of pneumatic fracturing. What we do here is we go create open boreholes either through augers or air rotary or sonic, and typically, we're only going to do this where the borehole is going to stay open, and we lower these high pressure packers into the target intervals that we've defined, and then we hit them with a dose of high pressure nitrogen gas, fracture the formation, and then we start pumping in the amendment. So typically in a tight clay, this is how we would distribute in a source area the EZVI. And on the left, you can see that just represents the nitrogen tubes that we use. And so that's a pretty common approach for us. We do a lot of just DVI injection with pneumatic fracturing in these finer grained soils. The other approach is just to go straight hydraulic, and here we initiate the fractures with just the amendment itself. So we'll initiate a fracture with the amendment, the EZVI, and then we'll just continue to pump the amendment into the fractures we've created. It does take a larger pump than you're probably used to. This is you may have seen campground pumps out there. This is They're chemical on steroids. It's got a, I don't know why this is moving forward. It's got the capability of injecting at 50 GPM at 2000 PSI. It's electrically driven. We don't really need that much PSI. It's a fracture, but we do have a lot of pressure loss in our lines until we get down to the target interval in the formation. So most of that pressure is just to move the that slurry through the injection lines. So we've done a lot of tests with this over the years. We've worked with NASA during the initial pilot testing, and we did some direct push high pressure injection at multiple projects. We've done a more focused hydraulic fracturing at sites in California, where we targeted PCE, and then we've done the source area with the EZVI at a dry cleaner. Then we've gone down gradient with emulsified oil, and we've bio-augmented with KB1, a T. helicoides product. We've also done a chemical complex which had PCE and carbon tet with EZVI. And as you know, carbon tetrachloride is a pretty recalcitrant compound to treat, and really isn't amenable to any other approach except chemical reduction. And then we also did a carbon tet project in Nebraska at a soybean refinery, which I thought was kind of interesting because they made soybean oil, and we were using soybean oil in the product, and they had contaminated the site with carbon tet because they were using that as a fumigant or something for products stored at the, which is a big problem in the Midwest. Most of the grain silos use carbon tet in the past, and for the grain silos, and it leaked into the subsurface, and now the Department of Agriculture has a big mess on their hands of trying to get all this stuff cleaned up. We've also done some pneumatic fracturing at Patrick Air Force Base at a TC source area. So we've had some good experience over the years. Recently, we just early this month, we just worked on a dry cleaner in Indiana, and we did it was a pilot test, but we did some EZVI in the orange circles, and then we did another product, a peroxychem Avonic product called Geoform ER, and that was not in the DNAPL area, but in a higher concentration where they needed to go chemical reduction. So we just completed this. I thought I'd share it with you. It's kind of what it looks like. That's the material being mixed. So you can see it's like a chocolate pudding. You definitely don't want to get it on your clothes. You'll never get it off, but it's non-toxic. We do inject it through direct push. We can't inject it through wells. And we do get back pressure when we inject into the subsurface. So we've always got to be able to vent our lines and bleed off the back pressure. And the way we do that is not to remove the rods until we got a good indication that the back pressure has subsided. And then on the right there, we just show, in this case, we're also bio-augmenting. So that's a canister of KB1 that we're using to bio-augment as well. Because like I said, with the amount of soybean oil in the product, we are going to get some daughter products. And so we've got to take that contingency. There's a little more on the project. You can see there it is in totes. There's the injection setup, the pump, and the injection area. And just to give you an indication, this product sells for $20 a gallon. However, with the supply chain issues going on in the country and the price of scrap steel going up, the price has increased to $25 a gallon. And also the price of soybean oil has gone up. So we expect that to go down as everything gets back to normal, hopefully sooner than later. Got a couple of videos here. Illustrate the pressure as the piston pump is moving. And you can see there we're getting to high is about 400 psi. So like I said, a lot of that is just pressure loss through the piping and the injection hose. But generally, we don't need that much pressure to actually fracture. It's usually a couple psi over the depth of the overburden. And then over here we have another picture of the mixing. So here's a summary of the report that is typically how we report the injection of various chemicals. We've got the amount of products, the injection points, the amount of product injected, and then the total gallons injected, and the amount of dihalococoid liters injected as well. And then we do that per day and the number of points completed. And then we totalize those. So it gives a good idea of the volumes required and the amount of time it takes. So this was basically, a 7-day project and averaging somewhere around 5 locations per day. Now, and if we get into the details of injection, what we're really interested in this case, we had a target interval of 25 to 15 feet. We're targeting 2-foot intervals. In this case, we're going bottom up. We've got our initial pressure to fracture, so you can see kind of where that is. And then the sustained pressure to inject once the fracture is created. What our average flow rate is. We can measure flow through mag flow meters, or we can measure them by volume reduction over time. And then the amount of amendments that are injected. So that gives you a good understanding of when you go back and try to evaluate the project, the performance at each injection point, and whether or not it was within the design parameters. So a couple of case studies here. These are case studies from our partner TA that they've shared with us. Like anything, it's always a little difficult for companies to get subcontractors to get case studies. But in this case, they've got a few here because it is unique technology. So this is a nice rail car crash, not a crash, but a accident in Louisiana. And it was a big deal at the time. They had to excavate a lot of material. It was moving a lot of PCE, so a lot of PCE pure product was dumped along the rail. They immediately excavated, put in a slurry wall, and then they ran a pump and treat system for 30 years. And they also had some sumps that they created to capture, some of the PCE. But the DNAPLs still remain. They still had free product. They had matrix back diffusion issues, so they weren't going to turn that pump and treat off, in our lifetimes. So in 2013, the sumps were treated with source kill, and then after 2 years, a closure request was submitted, and then in 2016, the site was closed. So that was a good success. This is just a cross section of where the EZVI was injected, and they were able to get a risk-based closure for the contamination that was in the clay. So like anything, there's a lot more detail in a case study, and And the devil on these is always in the details. But in this case, it was an effective way to directly go after the DNAPL and make some good progress over the high cost of pump and treat with a source area that hadn't fully been remediated. And here's some of the results. So you can see here, there was once the EZVI was injected in 2013 timeframe, they had a really good reduction in PCE and monitored for a long enough time to address any back diffusion or rebound issues, and we're able to close the site for the client and estimate save some significant dollars by not having to run that pump and treat system. So, and this is a typical application where you could use an EZVI source scale product where you've got a pump and treat system, you really haven't gone after the source, you're going to be running that pump and treat system forever. You've never felt it to be cost effective to go after the source, or you may have looked at thermal, which we do provide as well, but thermal was too expensive, and so you're kind of stuck in the pump and treat forever scenario. Here's another one where they had a pump and treat system. This is at a tank farm that had PCE and carbon tet in the subsurface, and they had those contaminants discharging into surface water. And so they had to put a pump and treat system, recovery wells, and we're tasked by the client to can we shut these things down. So first did an MIP investigation to really understand where the DNAPL mass was, and then went in and injected the EZVI source kill. So there's a bunch of MIP locations and the EZVI locations where the injection occurred. On the right is the MIP data, and so we've got conductivity data, and we've got the PID data, or the XSD data. So I've got a good understanding of where the DNAPL is, what the lithology is like, and so you could go in with a pretty targeted approach of fracturing in the EZVI to treat that material. And based on that, they developed a target interval of about 25 to 50 feet. And once again, they were able to show, pretty good results starting in 2014, and eventually, getting down to concentrations that allowed the client to turn off the pump and treat system. Just another good example of how you can use a good source technology to give you a shot at turning off a pump and treat system. And then, like I said, this technology was developed by NASA, so a lot of projects in the Space Coast, which is also Cape Canaveral, Cape Kennedy. It's got all kinds of names, but outside of Orlando there. And they started out with 800 milligrams per liter of TCE. So no matter how you look at that, that's a DNAPL range. And they were able to make a big dent in the source area, and were able to go from removing the plume to a less onerous remediation strategy for the lower concentrations. So key takeaways today. What's the sweet spot for this technology? It's right up there in the NAPL pools to the ganglia. So that's where it's going to provide, or actually to the droplets, the best bang for the buck. Thermal is, obviously there's some overlap there, but thermal is generally going to be applied up to the ganglia. And whether or not you choose thermal or EZVI is, just a decision based on, the complexity of the site, the amount of DNAPL, the lithology, and so forth. But, thermal is the big hammer, but EZVI follows right behind it as a viable approach. And then you can see the other technologies kind of where they fall into place. So just ISCO or ZVI, really going to be in the droplet or the absorb dissolve phase. And you can see ISB or in situ bio's got a little less, less concentrated target area. And then ultimately, we start getting into M&A when you're in these trace areas. The other thing with any injectable compound is the methodology for applying it. It's not just the chemistry. We know that for years of injecting chemicals on the subsurface and seeing what happens. So we highly advocate getting a good high-resolution view of the site, and we call it high-resolution design optimization. So you're going to better understand where your contaminant mass is so you can develop a targeted strategy for that. Based on that, you can develop a design including a radius of influence, both vertically and laterally. And especially when we're injecting these type of compounds, we really want to get a good feeling that we can achieve the radius of influence. And so we call that the design optimization testing phase. And that's really where, based on everything we've done up to that point, we know that we can get the delivery of this amendment to where it needs to go. And so that's a critical step, because if we're not, then everything else isn't going to work. And then once we've gone through that phase, we're ready to go to full scale and eliminate any big surprises or remobilizing, or no, that we can't distribute it properly. We got to go to a different amendment. And believe me, we've worked on a lot of those projects. So any chemistry, but particularly with this one, this is the methodology that we think will optimize remediation and as well as cost. So other key takeaways, if you weren't familiar with the original nanoscale EZVI of the past, today we have, the cost has gone down because of the microscale ZVI. So that's a positive for application. In the past, it was generally traditional sampling to try to delineate the DNAPL footprint. Today, we can do a much better job, cost-effective job of doing that with a high-resolution design optimization technologies like the LIAPG. Originally it was thought that we just would inject the EZVI in massive pools of DNAPL. But we're now seeing that we can actually expand the application to the residual DNAPL and the ganglia and still get good cost benefits from that. So we're not just stuck into the a big pool of TC in the ground. There's I think a little less source confusion in the past. Folks have been attacking DNAPL with ZVI and a bioslurry, ISCO, in situ bio, surfactants. And over the years, based on what I've seen, the emulsified zero-valent iron shows the highest efficacy. The other ones, I think, were wishful thinking and lower cost, but at the end of the day, it didn't really make a dent in the problem. We're also seeing vapor intrusion wasn't as big of an issue when the technology was first rolled out. But as you know now, it is a big issue. And some states that we work with, the regulators are also requiring treatment and not just a mitigation system. So I guess like LIAPG, you've got to remove the solvents to the greatest extent practical before you can just rely on a mitigation system, which to me makes sense. I'd like to know that if I, bought a house or property on top of a TCE plume. Rebound, I don't think rebound was very well understood in the past of whether or not it was occurring from sorb mass or DNAPL, but I think we understand that better now, and it gives us a better basis to actually go after the source material, since we don't want to be chipping it away at the iceberg for years and years. Originally, EZVI was applied by itself. There wasn't a lot of concern over DCE or vinyl chloride generation. I think now there's a little more sensitivity to that based on geography and regulatory scenarios. But I think now we've realized that we've got to bio-augment it at the same time. But we're also going after a much lower percentage of breakdown products because primarily we're going through a beta elimination pathway. And then the PRB strategies. In the past, PRBs were put in and they sometimes require redosing, but they weren't going to last forever. And now to create less stress on the PRB and hopefully not have to go out and re-inject or reapply, the source treatment is just going to put less stress on the PRB performance. So those are kind of key takeaways that I think are driving more of the adoption of source kill EZVI going forward. And that's it. Hopefully that made sense, and I'll be glad to take any questions.
Anyone who has any questions needs to unmute themselves.
And Cascade is offering a free trip to Hawaii to the first question. Just kidding.
No questions at all? Jennifer, can you make sure that you can unmute yourself? We don't have some glitch.
Can you hear me?
Okay, yeah, good. Okay.
If anybody has any questions, they don't have a microphone, they can feel free to use the chat and we'll read the question out loud for you.
Well, Elliot, I think you did too good a job.
Yeah, that's good. So I've got an order form I'm going to post, and so you can order the product right now and you can get it delivered. So.
All right, well, while we're waiting to see if anybody thinks of any questions, I just want to say thank you again so much. That was a really nice, interesting presentation. It was very informative, and we very much appreciate you doing this, and would love to have you back sometime if you've got another one on slightly different topics.
We have plenty. We have plenty.
Okay. All right, great.
All right, well, thanks for the opportunity, and I'm gonna go out into the hot Texas muggy weather here and get something to eat.
Thanks a
All
lot,
right.
Elliot.
Yeah, no, you're welcome.
Thank you, Eliot.
Yeah.
Thank you, everyone. Thank you very much for participating tonight. This was awesome. Nice turnout, and hopefully see you next month.